My name is Zac Sweers. I'm a mobile engineer at Uber on our mobile platform team. Our team basically builds a lot of core framework components, foundational stuff to not really work on any specific feature, but more to enable all the other developers that we have in the company to work as fast as possible. And this talk has nothing to do with anything that I work on at Uber. So this is actually a pretty interesting talk in the sense that most of the talks here at this conference are things that you should know about and learn about and things that you should do, and this is not anything that you should ever do. If you take nothing else from this talk, please take nothing. So without further ado, let's talk about ClassLoaders. All right, keyboard it is. So there we go. So first and foremost, a class loader is itself a class. It's been there since Java 1, and it's a simple class with just a handful of methods for basically just pulling out various things. For the scope of this talk, we're just going to focus on this load class method. Now, class loaders are an abstract, class loader is an abstract class that can have any number of implementations. A conventional one that's often seen is URL class loader, which just loads jars or loads from jars or directories, or in this case, the URL is the URL to the container of classes. This is not actually what Android uses, but we'll get to that a bit more later. Amusingly, though, AOSP did seem to at least think about it at one point. I don't know if you can see the comment here, but it says, make this Java net URL class loader once we have those, with a question mark. Another thing to keep in mind is that they follow a delegation model. So what that means is that every class loader has a parent that it defers to. In fact, on newer versions of Android, the parent will actually always get first pick. So even if you have a class loader that has some custom handling for a particular class, if the parent says they can handle it, your class loader is never going to get a chance to it. It can be null, though. It is optional. And at the JVM level, there's a boot class loader at root that has no parent. So if you look back at that previous example, that's this last argument going in here. So what happens at runtime? When a class loads, it comes through this load class method. And we're going to go through a little tiny example here to kind of illustrate how that flow goes. So we've got this foo class in here, and it has a process for this. You can't really see it in a stack trace, but if you have a class loader and you were to breakpoint it, you'd see these coming through, and this gets handled basically at the framework level for Java. So, or the VM level, I guess. And when we load foo, it comes through class and looks something like this. You see this fully qualified name, example.foo, and it's asking you to load that. But foo isn't the only class here. Bar is also a thing, and it needs to be loaded as well. And when bar is loaded here, it's loaded in the context of foo. So what I mean by that is that it actually goes through foo's class loader to then load bar itself. And it'll continue this transitively for any other classes that come through this. Note that this is done as code is hit, so it's not like you're going to hit everything up front. So a good example of this is if you have an anonymous inner class with some methods in there, those methods are not strictly going to be hit whenever you load up the class that the anonymous inner class is instantiated in. And now, what about Android? So as we saw earlier, Android doesn't use URL class loader. It instead uses a path class loader. Now, path class loader is a simple class loader that accepts a path to a directory of DEX files. So this is what's used for the system and application class loaders by default, and it's actually one of a few different kinds of class loaders that are available in the framework. Another one is DEX class loader, which seemingly from all the research I did works exactly the same way, except it has an explicit doc saying that this is what you should use to run code that was not specifically part of your application. And both of these extend a base class called base DEX class loader. Now, base DEX class loader is where the main implementation lives, but it itself is also fairly simple. Beyond this point, though, it gets a little bit into the nitty-gritty of how framework code works. So under the hood here, you've got this class called a DEX path list. Under the hood in there, it in turn manages and delegates to a bunch of what are called DEX file objects. And these are backed by individual DEX files on the class. Interestingly, DEX file itself is public, but marked as deprecated, even though it's used everywhere. And DEX path list is not. So that's it. But wait, the talk title is Breaking the Android Class Loader, and I've only just told you how they all work. And I promise we're going to get to that, but first I need to tell a quick backstory. So this is Utkarsh. And he works on our scaling team. So he spends a lot of time on things around startup optimization, class loading, basically, how do we make our apps work well on devices that aren't the latest Pixel or, things like that. And I really wanted to get him to do this talk with me because this is very much a sort of like, I don't know, long-term pair programming exercise that the two of us have worked on. But a few months back, one Friday night, it's about 7 p.m. or so, I was in the office a bit late and about to head home, and Utkarsh comes over to my desk and he says, "Hey, how's your reflection chops?" And I said, "I don't know, it depends." He says, "Okay, can you help me with this thing?" And so we go to his computer, and for the life of me, I can't actually remember what specific thing he was trying to do, but we were working on it, and I asked him what his larger goal was for trying to do that bit of reflection. And he said he wanted to create a class loader pointing to DEX files so that we could then manually load classes out of that and use that to instrument how long class loading takes. Because we knew that we were seeing startup time issues that seemed to be related to class loading, but we had no real means of instrumenting it other than potentially building our own custom ROM of Android and having it log out things as it's coming through. And so, like I said, it's a Friday night, our beer tap's open at 6 p.m. So I made a joke to him that rather than trying to manually do it out of our own class loader and replicating some environment, we should just hijack the application class loader. And Utkarsh is the kind of person that hears that and says, "Okay, yeah, let's try it." And so that's what we did. So the first step to try to figure out how we could do this was to look at the ClassLoader class in IntelliJ and find usages. Now, that's a lot of usages and not something that we were going to get through on a Friday night. And so that clearly wasn't going to work. So we tried a different approach to see what ClassLoader was in place at runtime, which yielded something that hopefully is visible. That looked bigger on my screen. But basically, when we breakpoint something in our application on create, and we're running in the main thread, and we ask the thread what its class loader is, we can look in here, and it says something about a path class loader, which, hey, we've actually seen that before in our screenshot earlier. So now we're on the right path, and after looking around at usages of this in AOSP to try to get a sense for how it's used, how it's constructed, etc., it turns out that all you need to do is point it to your app's source directory, which you can just call on the context, get your application info, and there's a source dir field. And then that's it. You can also pass it a parent, but you don't need to necessarily. And you can construct an instance with that, and now you've got a fully functional class loader using our APK's DEX files. Now we could take path class loader and extend it to make our own, and then we can drop in this nice convenient log statement to basically say every time we load a class coming through here, log it to logcat, and then we could quickly try to put this in different places and just look at logcat to see if it's working. Now, in the quickest way that I can put this, we tried to do this in a ton of different ways. So we kind of, again, went back to where are there class loader fields and how can we reflectively replace them? So tried a ton of different places. The first one that we tried was the system's class loader field, which basically in that top level class loader class, there's another class loader inner class of that with a loader field. This was just eyeballing AOSP. That didn't change anything, and also on Android P, this just totally stops working, and we're not sure why. So the next thing that we tried to do was set the main thread's class loader. So you got that get context or get class loader from the main thread. You can also call set somewhere in there. So we tried to do that, and then that didn't work either. We got close to giving up by this point, but then we found this class called context_impl in AOSP. Now, this is a great class to look at in Android Studio because literally all of it shows up as red because everything is @hide annotated, and it's really frustrating to try to dig through. But context_impl, in a nutshell, is the base context that all other contexts in your app end up wrapping around. So every time you have an application, an activity, etc., all of that is basically just context wrappers with this at its base. If you keep digging deep enough into, I think it's get base context on a context class, you'll eventually hit this. And this is really where all the magic happens. It holds your resources, it holds everything relevant to your app. And in here, it has a mClassLoader field. So we tried that, and it didn't work. But we got a different error this time. We actually got a field not found exception, which is really confusing because we were looking at it in AOSP, But yet, when we looked at it here, it said the field wasn't there. And when we jumped in the debugger, same thing, the field's not there. And yeah, we were really frustrated. And then Utkarsh takes a step back and he says, so you're running this on an S8, like a Galaxy S8. What if we try a Pixel? And sure enough, the reflection works there. So thanks, Samsung. Even when we're trying to do bad things, it still fails. And so we tried that, and it actually ended up still not making a difference. I think we saw one random log come through, but it was clearly not everything that we wanted to see. So again, we were pretty close to giving up at this point, but at this point it was maybe like 10 p.m. or something. And again, on a Friday night, so like I was trying to go home 3 hours before. And we tried a few others that we had found, again, to no avail. But then there's another interesting field in this context impl called package info. Now, package info is a type of class called loaded APK, which is another one of those add-hide annotated classes that you're not allowed to go look into. But we see it in the debugger, we see it in AOSP, and it too contained a class loader, specifically a path class loader. It's actually initialized with one under the hood. So we go digging in there. It has this class loader field inside of it. And when we set this with reflection, then suddenly everything worked. There we go. I knew I was going to forget I put that animation in there. So now, as soon as we start up the app, we see all these classes coming through our logcat, and we've got this instrumentation working. And we've successfully basically hijacked the class loader of our application. So we've got, kind of overview of this is now we've got a custom class loader that can point to our dex files and run our code arbitrarily. We can, instrument it however we want. It seems to work. The application was able to run. We did this in a sample app for an open source project that we have that was easy to run with because it built very quickly. We have an installation method now through this reflection approach. So now we've got this thing that's doing a bunch of morally ambiguous reflection and runs on your phone. So naturally, we call this Black Mirror. And that's the story of that Friday night, and that leads into a series of demos that I want to show you of what you can do knowing this information about how Path Class Loader works and working with dex files under the hood. So, without further ado, if you want to follow along with this code, it's all on GitHub at HC_Sweers/Black Mirror. This is also my first live demo in a conference talk, so I fully expect disappointment. And now I need to make this a mirrored display, so bear with me for 1 sec. All right, so the general structure of the project is we have this Black Mirror. I don't think I have time to really talk about this init provider. The short backstory of this is that we wanted to install it as soon as possible, and there's a clever trick that you can actually have code that runs before application on create by hiding it into a content resolver and then packaging that, and then all of that will get run before application on create. But the main interesting point here is we have this Black Mirror class. So this is basically a sort of, polished version of what Utkarsh and I put together a few months back. You have a few different checks for some API differences that we had noticed. It extends Path Class Loader like we designed. We actually built a little interceptor API that I'll get into a little bit later. And you've got this install method. And this is where it goes through and basically tries to replace every class loader field that we could find. If you look through here, you'll see a lint that says, hey, this is a private API. And so we will double click on yes and continue on our way. And and then here's the Samsung code that doesn't work, which is great. So we've got this Black Mirror class. We have this demo Black Mirror app here that I'm going to show a few different examples in here. Got a few activities, and the first thing we're going to do is look through some interceptors. So that interceptor API that I was talking about here, if anyone here has ever used OKHTTP, there's an interceptor API in there that basically you get a request, you can proceed on a chain and get back a result. This is designed basically the same way to see what you can do with it. And the first example that I want to show, I'm going to close this out for more real estate. So the first thing that I want to show is log interceptor, or logging interceptor. There it is. So this is a super simple interceptor. You can basically just drop it in and intercepts a chain, and then when you get that, you say, we're loading this class, log it out to Timber or something, and proceed. And you're done with it. Another variant of this, so this is useful for like instrumenting class loading, especially if you're trying to optimize startup time. The next thing that's worth looking at is a timing interceptor. So this is basically an extension of the logging interceptor where you're actually recording the amount of time that it takes to pull something in and out of a class loader. So these were the two main motivations that Utkarsh had on that day that he was trying to use for optimizing. But we can actually take this so much further, and this is where the talk really starts to get fun, hopefully. So what if we wanted to do something a little bit unorthodox? So what if we wanted to say, has anyone here ever used or looked into how AppCompat does replacement for AppCompat widgets? All right, oddly, this half of the room. So the basic gist of it is in AppCompat, if you have, say, like a text view in XML, then when it sees that during layout inflation, it'll replace that with its own AppCompat text view so that you get all the backported theming and tinting and all that. And we're going to try to do the same thing, or you could try to do the same thing with this request swapper, and I realize that my doc here has given away the joke. But we can actually say, hey, when this is trying to load a text view, what if we actually say want to return a button? It's a subclass, so it's a valid cast to do. We want to see if we can actually hijack this. And it turns out that the answer is no, because if you go to this J&I code somewhere deep in AOSP, there's something that actually checks to make sure the class that came out is the class that you requested going in. And if it's not a match, then it actually rejects it and says, hey, your class loader is lying to us. So the framework's on your side a little bit here. You could also try this with just intercepting the result. So you can go into a result swapper, yeah. Which basically just when it sees a text view, it instead just tries to load the button class directly. You could also even try to fake this with a proxy. So proxy class or proxy APIs in Java are just, you can take an interface and then return basically a fake implementation of that and handle invocations directly. This fails for a different reason that I wasn't able to actually find the source of in AOSP, but basically the framework is at least watching out a little bit for deceitful class loaders, I guess you could say. So the next thing that I want to show is something that actually there are a few apps out there that do this, and that is actually packaging in code separately from your installation. So what do I mean by that? So say we've got hello, I've got a lot of things in here that say hello. There we go. Say we have this hello interface. So this is in a separate project. It's just a simple interface, has a method, say hello, returns a string. And somewhere we have this this hello implementation that says, hello, this is loaded from somewhere. And then we've got a couple of examples that I want to show you here. So some prior context to this. So there's another API that is also not public that basically in base Dex ClassLoader, there's a hidden constructor that takes an array of byte buffers and a delegate class loader. Each byte buffer in this array is just a byte buffer representation of a Dex file. So you can load that however you want. All it cares about is that you have the buffer of bytes at the end, and it creates a class loader that delegates to all of these under the hood. So if we can get a stream or access to basically a byte representation of the given Dex file, we can pass all these in and start loading classes out of it. So using this, we can actually go into asset helper. So in this, we want to say we're going to package in a Dex file in our assets directory. So this would just be as simple as making a compiled version of that hello implementation and then running the DX tool over that to generate a Dex file and dumping it in our assets folder here. And with this, our load, we can actually load up this Dex file as an input stream from assets here, and then create a byte buffer representation of that, pass that into the hidden constructor for a path class loader, and then we get a fully functional class loader wrapped around that Dex file. We can then reach into that Dex file, ask for the hello implementation class that we're looking for, and start doing things with it. So if I go look at where this is used in our assets activity, we have a text view in here. We load up the hello implementation, call new instance, It's an instance of our hello interface, and we ask it to say hello. Go into here. We'll get to this more later. And there we go. So this is actually loaded directly from unpackaged code, or I guess it's packaged, but not in your AP, or not classes.dex. And you're now actually effectively side-loading code from your own packaged assets. You can do the same thing with resources. So if we go to resources activity, you can do the same thing here. We've got a resources helper. It looks almost identical to how assets work, except that we stick it in the raw directory. So if we look in here, we've got this hello info.dex. We pull this as an input stream out. Again, do the byte buffer loading, get the byte buffer, get an instance of the class loader, look for that class, and then in here, we can pull it out, create a new instance, cast it to hello, go into our resources, and now we're running code that we've packaged in our resources. And this could potentially be useful, I guess, if you want to use like resource splits. So maybe you have like a nighttime hello and a good morning hello, or I don't know, use your imagination. So also, I forgot to mention this earlier, but we can actually go through and look at logcat and see our timing and logging calls coming through here. And I don't actually know what the correct unit is to use for timing these, so I went with nanoseconds, but you get really big numbers. So yeah. Now, the last example, or set of examples that I want to show you involves this neighbor app that you might have seen here. So this is a separate app. It's just called Neighbor. It's fairly simple. So if we go look in the code for it here, we've got a couple of classes here, just a simple main activity, has an API in there that's just like a simple retrofit API. And in this main activity, we have this say hello static method that says hello neighbor. Now, we know from our earlier investigations that all you need to do is point path class loader to the location of an APK. Now, that application info that we use to read our source directory out of, has anyone here ever done like intent resolution or looked for other installed apps for some reason? So you'll know that that gives you an application info instance as well, which also has these source directory fields. So I have this little helper class here called spies. And you can give it a target package name. It goes and looks up the location of that package using the package manager. You start iterating over this app info list. You run through, you find the one that has a matching package name. You pull out the source drawer. You pull it back here, you pass that into the path class loader, and now you've got a functional class loader pointing to someone else's application. So if we go into our hello activity, so we have something here that runs into this spy helper and just says load the class loader for my neighbor app, load that main activity class, and find that static hello method. We run back in here, run that sample, say hello, and now we're running our neighbor apps code with no extra permissions required. There's nothing in my manifest saying that I'm allowed to run other apps code. There's nothing, like this is not a rooted emulator. This is totally legal Android code, and any app can do it. So we can take this a few steps farther. So that's a fairly innocuous one. It's running in your process, so it's not like you can like go and like DDoS their process. But we can also potentially start doing some not so nice things with this. So I've got another helper method in this spies class that basically looks through available classes in a class loader and sees if any of them look like a build config. A build config is where you have a lot of standard Android stuff, but it's also where people tend to put a lot of like API tokens. And so in here, we want to load up a class loader, and then under the hood, we actually want to dig out that array of dex files. So we have to do some ugly reflection here that you just have to trust me that this works. And then we go through these dex files, and then we start iterating over these elements in each one, and each entry is just a fully qualified class name. And we can pull out that class and start looking through there and see if we can guess which class is a build config. You can also just take the shortcut like I did here and say, try to load one that is just called the package name plus build config. If it's not obfuscated, chances are that'll work. And as it happens, that is exactly what we can do here. So in this case, we point to the other app again, and we say, look for a build config field. And once we find it, we just go through and print out all the static fields and values. And sure enough, we can see everything in the build config here. And just to prove that I'm not pulling your legs, what's your name? Dan? All right. So if I go into my neighbor app here, and I say build config field strings, greeting. Hello, Dan. And now I can't see my run button. Thank you, Gradle. What? I want my run configuration. All right, hold on. I have to exit presentation mode to pull this up and switch. All right, so switch to our neighbor app, run this new build of it. Runs through here, looks pretty innocuous. Go back here, run the spy again. Hello, Dan. And then, yeah, so that was super easy. Didn't have to actually change any code. Again, just looking up code as needed dynamically in here, and it's kind of shockingly easy. So what if we want to take this a couple steps further? So in our neighbor activity here, we have, let me put this back in presentation mode. It's not being full screen. So we have the simple retrofit interface in here called a neighbor API. It has a few different methods, like this post image that has a hard-coded client ID header on it. It has this get super private info endpoint, has this create user endpoint, etc. Now, if I know where this class is, or if I just write something that works like that build config searcher that just looks for interfaces that have retrofit annotations in them, I can very easily run in here, go peek at another app's code, and then start printing out the stuff that we find in their services. And to take this all the way over the line, we can actually go a step further. So if you've ever used retrofit, you can create a new retrofit instance, and then there's a create method where you just give it a class, and it gives you back a full instance. We can actually go through here, borrow activity. Sorry, it's a bit gnarly with the RX code here. But we can go through here, create an instance of that service. We know the method post image. We've got an image that we're going to upload in here. We call that. And if I run that here, I'm now running this other app's API from my app with no permission issues, no sort of hesitation. It all just kind of works. And we've now uploaded an image to their API without asking first. So, yeah. Is there anyone here who does this? All right. Surprisingly, I see 2 hands. All right. Who here uses Play Services? Congratulations. You all do this. This is what Play Services does under the hood. It's if you turn on strict mode and watch what happens on App Startup, you'll start seeing it loading a bunch of DEX files. Actually, a good clue for Utkarsh and I when we were looking into this was when we tried to look for usages of base or path ClassLoader, we found one esoteric usage deep somewhere in Play Services basement. And so that was kind of a canary for us that we were on the right path for it. Now, another thing you might be looking at for this is, gosh, that seems really easy. Like, kind of trivially easy. What if an app shipped with a decompiler in it and just started reading our classes out of there? And you'll be happy to know that you don't have to go do this yourself, because one already exists on the Play Store, and it's called Show Java. And you can pull it up, pick from installed. It pulls up a list of your apps. You can pick any number of decompiler of your choice, and it can go through and start decompiling your app. Or it can fail, because, of course, that's the last part of the live demo, and that's when it, okay. Yeah, so that's on the Play Store. You can check it out. It's a little bit scary that it's this easy. And for this last part, we'll go back to the presentation to do some final notes. Let me switch this back. There we go. So, like I said, you can find, you can find all the sample code on the GitHub repo. Some final notes to take away from this is that some good news, I guess, in this is that it is a lot harder to do in Android Pie. So there's this project called AppCompat, which is not confusingly named at all, that has nothing to do with the support library AppCompat, and this is around not accessing private interfaces. So all that Black Mirror stuff with like trying to replace ClassLoaders at runtime with reflection, that doesn't work anymore. But all the path ClassLoader stuff is still totally fair game. You can still look at other app source code. You can start running it if you want. If you ask a security researcher, you'll probably get an answer, something to the effect of, well, it's fine because it runs in your process and not theirs. Which, yeah, but it remains to be seen if this is actually something that should be this easy. Actually, my manager would probably want me to mention this. We don't do this at Uber. I see you New York Times people over there. We don't do this at Uber. Just want to mention that. The second point that I want to toss in here is to be mindful. So what I mean by that is that it's one thing that it's once you ship your app, it's fine. Like you know that you've put it out in the Play Store. Anyone can go to APK Mirror or something, download it, decompile it on their computer, go look around, do whatever. That's sort of like an accepted part of doing Android development. But this is actually kind of a different spin on it that a friend of mine actually pointed out to me that, say you're working on some new top secret project and you've got this unobfuscated pre-release debug build running on your app, and some other app decides to go look at your source code. They can actually read your whole APK, and they could do that without requesting permission. You get no notification from it. They can send it wherever they want, conceivably. It's something to keep in mind. Not saying that everyone should wear the tinfoil hats, but it is, you want to be mindful of this stuff. If you've got super secret stuff, you maybe want to be aware that this is easy to do. If you looked at this and thought, wow, there's a lot of opportunities here, then I'm concerned. And that's it. Thanks.